Hey logical people, GKB here. This video is divided into two parts. Part 1 is about learning the advanced machine learning concepts, of course building upon the 6 steps of machine learning framework that we learned in the previous video. And once you are comfortable with the advanced machine learning concepts, step by step we're going to build upon the model ensembling techniques. If you're in a hurry and only want to understand the ensembling, feel free to jump ahead. Alright, without further ado, let's get started. Alright, and this is the notebook we will work on to run advanced machine learning concept. And before we run the bagging concept, I would like to talk about following topics. So we're going to talk about normalization. What is normalization? How do we do it? Transformations, target transformation, bin numeric variables, assembling of course, and then logging the experiments, okay? So the step one is basically to install PyCaret. I have specified a version here, but if you want, you can just run it without the version. So I press Control and Enter, and this will download and install PyCaret on my Google Colab. If you're running it on your local machine, make sure to have PyCaret installed. Okay, PyCaret is a big package. It takes a lot of dependencies, so it might take a while to install everything properly. And once I install it, I'm pretty sure Google will ask me to restart the runtime. While it's installing, a big shout out and thank you to Google and PyCaret's team. They have done a tremendous job for providing everything as a packaged bundle so that you and I can just use it without being bothered about writing the code from the scratch. Okay, the PyCaret has been installed. I need to restart the runtime, so I'm going to just click on this. Now let's talk about the techniques that we're going to cover. So the first technique is called normalization. What this means is rather simple. So if I go back to Excel and let's say I have an age parameter in my data set. So let's say the age is so I've got age as values. There are multiple ways of normalizing your data. The one would be that you use the range and min max. So I'm going to say the minimum value is 10, and let's say the maximum value is 98, and the range is 98 minus 10. Therefore, the normalized age will be this minus the minimum value, of course. Then we divide everything by the range. And then you basically drag it. Oops. I'm going to lock a couple of cells, so this should not move and that should also not move. Okay, so now you see that this normalized data or normalized age still have all the data, or let's say all the data relevance within it. For example, if I look at this 87, normalized value is 0.88, and if I look at this, for example, 41, the normalized value is 0.35. So you still have the range difference for sure, but everything has been normalized between 0 and 1. And this is important because once you have a lot of features in your data set, and if one of the features have, let's say, a value of age which is 87, and let's say the other, let's say I'm running a machine learning algorithm for some sort of medical science study, and I have, let's say, magnesium in blood, and that is 0.001 milligram, right? Now this data is definitely very small compared to age, and if you use age as it is in your machine learning model, this heavy number 87 is gonna dominate the small number of magnesium in the blood. However, from the doctor's point of view, this is an important data, right? Therefore, we use normalization to bring everything to scale like this, and then we use normalized data set in our machine learning models. Okay, perfect. So enough of theory, and of course, using PyCaret, we don't have to do everything manually. The second thing is transformation, which basically means that so when we normalize the data, it removes the impact of the magnitude, right? So we just discussed about magnitude. However, there are some times that we have to use transformations so that the data, so the distribution of data is more, let's say, normally distributed. So normalization basically makes sure that the data is normally distributed. Okay. And there are techniques that we use for transformation. You can read more about in the link that I provided. So once you apply normalization and transformation, sometimes we want to use target normalization transformation, which is similar to transformation technique explained above, with an exception that it is only applied to the target variables. Okay. Again, I have provided the link. If you are interested, you can read about it. You technically don't need to know a lot about it, but if you have some understanding, that would be great. The next thing that comes into data preparation, and it is very important in machine learning because most of the thing in machine learning is about data, that we combine the rare levels, which basically means, and we're going to see that in our data set in a moment, if you have a distribution which says something like this, that let's say we have 100 students, out of 100, 50 are in second standard, 40 are in third standard. Now, when you start running your machine learning model, you technically don't want to have 6 different categories. You basically want to have 2 categories, which is significant for our data. And then you club everything into, saying others, for example, so that, this one data set do not influence our main data set, something like this. So all of these 4 will belong to the other group. Okay. And as I said, we're going to see all of this in action in a moment. Similarly, we would like to bin numeric values. So for example, again, we're going to see that very quickly in our data set. But conceptually, let's say we are calculating height of 100 students. So if I go and say height, and let's say I say random between, I don't know, 100 to 190 centimeters, and you technically drag it. Then you don't want to use, for example, height as 183, 151 as a data point, 156 as a data point, 100 as a data point. What you normally do is you say, okay, how many students belong to 100 and 120? How many students belong to 120 to 150? And how many belong to 150 to 180? And then, 180 and above. Something like this. You take all the data and then you bin it into different bins so that you can have better accuracy of your models. And then comes the model assembling. So we're going to look into that, of course. And eventually we would like to tune the hyperparameter. Okay, beautiful. So let's start with our data set. The data set that we're going to use is called Sarah gets a diamond, which basically means that while walking down the street, imagine you find a piece of diamond and you want to understand based on its weight, cut, color, clarity, polish, symmetry, and report, what could be the price of that diamond, right? And in our data set, we're going to have a carat weight, and 1 carat is equals to 0.2 gram. We have a cut, which is one of these 5 values. So signature ideal, very good, good and fair. There are 6 categories of colors, 7 categories of clarity, 4 categories of polish, and symmetry. Okay, so we're going to see that how we're going to use this data. So the first thing that we want to do is want to import the data, and that is also very easy thanks to PyCaret and the team. They have arranged this for us. So for timing, I'm going to say false. I want to import the data from PyCaret, one of this control enter. Now you can see that the data has been imported and the carat weight is one like numeric data. Cut is text, of course. The color is also text, clarity, polish, symmetry, report, and price. As you should notice that somehow we have to actually change this text data, the categorical data, into numbers. So we will basically go for one-hot encoding, and we're going to see that how PyCaret helps us doing that. But the most fancy, or let's say very intuitive thing that I wanted to talk about here, while you're importing the data set, you can actually say profile as true. And when you say profile as true, what PyCaret will do, it will go through the data and it will summarize the data for you. And that's become super helpful for us because, as I said, and I can't emphasize this enough, that machine learning is all about data. Everything else has been pre-coded for you. Everything is available for you to use. Your job as a machine learning practitioner is to bring data to life so that you remove the duplicacy, you remove all the noise, and you provide pure form of data that this machine learning needs. Okay. So now, since we ran this line with profile equals to true, thanks to PyCaret, again, they have summarized this for us. So if I go here, we have an overview which says we have 6 variables, 6,000 observations. There are no missing cells, got 78 duplicate records, and okay. So we have 2 numeric and 6 categorical data. Somehow we need to change categorical data to numeric, and we'll see that how we do that. Then we have, of course, 8 variables. So we're going to look into that. So carat weight, caret weight is highly correlated to the price, right? And then you see that we have 196 distinct caret weights. So minimum is 0.7, maximum is 2.91. Okay, makes sense. And here's the distribution. You can toggle the details so that you can see much more detail of this particular column. So here's the histogram. You can see that how the data is distributed and what are the common values. And as you can see that these are a few common values that we see in the data. And then we have 62% of the data, which is other values. Now it makes sense to bin the caret weight, right? So we just discussed, for example, here how we bin the heights so that we have better accuracy in the model. Similarly, it makes sense to bin the caret weights. And we're going to see how we do that in PyCaret in a moment. Okay. You can also look at the extreme values. So these are some minimum values, and these are 10 maximum values. And you also see the frequency and whatnot. I will leave it to you so that you can play around with the data. And I just wanted to point out the important things. Now, if you look at the second data, which is categorical data, so you've got almost, I would say, 70-80% of the data which falls under ideal and very good. And then good, signature, ideal, and fair has a very small data set, right? So it makes sense to bin them as well. But if it depends on you if you want to, if you don't want to. And for example, if having a fair data point is extremely important in your use case, you probably want to keep it that way. But that's the intuition behind it. Color has 6 distinct values and seems like this is distributed quite evenly, so this looks okay. The only thing is that it's a categorical data. We need to change it to the numeric. Now comes the clarity. Now you can definitely see that clarity has a very different distribution. So SI1 has almost 2000 values out of 6, and VS1 has very less values. So that is something we could technically bin it, right? We can bin these data into different bins. And then comes the polish, same story here. And as always, you can always toggle into details, and you can see what is the maximum, what is the minimum, what are the categories, and things like that. Yeah, I'm going to leave it to you so that you can play around with it. Just one quick pointer. I think this detailed view, or let's say profiling view, is only available in Google Colab. I'm not sure if it's available in Jupyter Notebooks because Google Colab is fairly advanced. So just have a look if it's available on Jupyter Notebook. Last but not least, if you look at the report, categorical data, of course, it has been dominated by GIA. So as a practitioner, you need to play around and see if it makes sense to include this data set. And then comes the price, and of course, as the weight goes up, price will go up, and we'll see all this in detail how each feature is dominating the price. Beautiful. Then comes the interaction. So you can see that as the caret weight goes up, the price goes up, and it makes sense that this is correlated. Beautiful. Now we can see some correlations. So you can see the price and caret weight, and there are Spearman's, Pierce, and Kendall. So as I said, I'm going to leave it to you so that you can play around with it. Here are some missing value data. So we don't have any missing data, so all good. And here are a few samples. So first few rows and last few rows. Here are some duplicate rows which are most frequent, so you can have a look around and have a better feeling of how your data looks like. And trust me, this is the most important thing that you need to do when you're running machine learning algorithms, that you need to understand how your data looks like. Okay. Perfect. So now moving on, and we have already talked about this, so I'm not going to go into this, but you can read about it. I'm going to put a link of this notebook in the description. So if you're on this, you're going to see data set. We have 6,000 rows, 8 columns. So the next step is basically to split our training and test sets. So I'm going to run this cell, Control Enter, and as you can see that what I've done is I have withheld 600 rows from the original data set randomly, right? So if you want, you can change the fraction to, for example, 80%, and then this data will change. So we are using 20% of the data as unseen data, but I think running 90% is good enough. And I'm using a random state of 786. You can use any state you like. If you use 786, you and I, we're going to get the same results. So it's always a good idea to match it up, okay? And then we are using 1,500, and then we are getting 5,400 rows for training our model and running all the algorithms on it. Beautiful. The next step, is an important step regarding PyCaret, is to setting up the environment. So in the beginners level, we learned how to initiate the environment variable using setup. We did not pass any additional parameters per se, because we kept every pre-processing as default. However, in this example, since we are learning the next level of customization, we're going to provide a couple of details into the setup. So I'm going to just import everything from regression. So that we have all the modules available. And then what I've done, I've created a dictionary of setup underscore inputs. You can name it whatever you like. Then I'm saying, hey, my target is the price column, which basically means that in this data set, if I copy this, come back here, and I say, you will see that this data set has a column called price. And that's what I'm saying, that, hey, my target column is price. So this price is what we want to predict. Session ID is 1, 2, 3, so that you and I have same randomness. We want to normalize the data. So whenever there's a categorical data, we want to normalize that. And PyCaret is smart enough to understand which data should be normalized, right? We want to say that please transform the data whenever data is not normally distributed, whenever PyCaret is running the relevant machine learning algorithm. We are saying also target transformation also true. We're also saying that combine the rare levels, which basically means that if you find something which is rare, so these levels are rare for us, for example, then combine these levels into, for example, a different bin, call it others if you may, and do that whenever the rare level threshold is 5%, right? And same thing, we are saying that in terms of multi-collinearity, that remove multi-collinearity between data sets. So for example, I think Investopedia has a really great example explaining what is multi-collinearity. And I'm going to scroll down to this example. If you're working on a data set which basically talks about body surface area and weight, then of course, if someone, or let's say some species, let's say we're talking about blue whales. So blue whale will definitely have a very big body surface area, which basically means that they will have a lot of weight. And therefore, you will see that body surface area and weight, they are highly correlated. And this high correlation between data sets sometimes create problems for machines to learn, or per se machine learning models to learn, right? So what we are saying to PyCaret is that whenever you find a high level of correlation, just try and remove that column from our data set. And again, we are always giving a threshold of 95% or 5% here, which basically means that whenever the correlation is higher than 95%, so in our example of weight, if you want to remove body surface area, we might have to say 88%, like this. Okay. So again, that depends on how you want to play around with it. We talked about this caret weight to be binned, because we want to bin caret weight into different bins, because as we talked about in our height example, these individual heights could be create problems for algorithm to learn. Therefore, we bin them something like this. And that's what we're asking PyCaret to do with our caret weight feature. Okay. So we have done all the input setup. So we have created a dictionary. Now what we will do is we're gonna create our setup like this. We are saying call the setup function, data is equals to data, and then we are using double star setup inputs, which basically means that this dictionary will be unfolded here as a parameter to this setup function. Okay. So I'm gonna run this, control enter. And when we do this, PyCaret will run a lot of processing. It will build all the pipelines for our data, which basically means that converting this categorical data to binary data, doing transformation, normalizing data, removing the correlations and things like that. Okay. And once it do that, it's going to give us a couple of informations on the screen. If you agree with the data types, so for example, cut is categorical, color is categorical, caret weight is numeric. If you agree with it, just press enter. If you don't agree with it, type quit. And then you have to provide this data type manually. So it's also giving you here. So I'm going to just press enter. And the processing is completed, okay? And these are the steps that basically has been used by PyCaret so that our initial data can be used in the machine learning algorithms. And these steps are technically called pipelines. So these are the steps that we take so that our initial data, which is this data, can be used within the machine learning models, okay? Beautiful. There are a few things that I would like to talk about here. The first thing is that, as you remember, the original data is 5400. We started with 8 columns However, the transform training set has 39 columns, which basically means that our transform data now have one hot encoding for all of these categorical data. That's one thing to understand. Second thing is that out of this 5,400 data points, we have a training set which is 3,700, and then we have test set which is 1,600, which is basically 70% and 30% split between training and test set data. Okay. You can also change this in the input setup. So here you can also define what could be the ratio of training and test. And if you're not sure how to find that, what you need to do is you need to go to Google, say PyCaret documentation, go to PyCaret, go to regression, since we are running the regression. And in this setup, we should be able to find the ratios. So if you go here, there it is. So you can actually define train size. I copy this, go back to our machine learning here. I'm going to say, my training set should be 90% of my entire data. If I run this and then I run the setup again, you should see that this data should change. I'm going to press enter because all the inference is correct. And now you should see that the training set is 4,800 and the test set is 10% of the original data. I'm going to keep it to maybe 80%. So I'm going to keep it to 80-20. Once you're happy with the setup, what we will do is we're going to run models command so that we can see which all models are available within the PyCaret. So as you can see, there are I think 25 different models available within PyCaret. And what we need to do is extremely amazing how PyCaret has been designed. What I can say is that, hey, I want to compare all the models that you have. So basically all these 28 models, I want to compare all of them with my current data set, which is this, and train all these models on my data set, and then tell me which one is the best. And I'm using n_select parameter for compared models so that I can get top 3 models. So I'm going to run this. And while this is running, I'm going to go back to the documentation. I'm going to search for, compare_models. And within compare_models, you can read about that. So if I can zoom in, this function trains and evaluates the performance of all estimated variables in the model library using cross-validation. The output of this function is a score grade with average cross-validation scores. And I've talked about this function in detail in the beginners video. So if you've not watched this, I recommend that you go and watch that. If you just run compare models, it's going to spit out one model, which is the best model. However, if you notice, we have used ensembling parameter in our execution, where we are saying, give me the top 3 models, for example. And we are also using another functionality where we are saying exclude ransack, which basically means that this random sample consensus model will not be trained when running this compare models. Okay. So I think this has been completed. Now, if we go and run print top 3, we will have a list of 3 models. So the first one is power transform target regressor. The second one is random forest. And third one is hover regression. Okay, so we've got 3 different models. If you want, you can pull out the first model. So you can say top 3, 0. And this should print out the first model. Okay. What I wanted to talk about super quickly before we go there is, when we run this compare model, it also gives us this cross validation matrix, where you can see that the top model is light GBM, so gradient boosting machine, which gives us the minimum MAE, then random forest, and then the hover regression. So these are the top 3 models, and these are the top 3 models indeed that you see here. So regressor, random forest, and the hover. Okay, beautiful. All right, now since you understand that the compare model gives us 3 different top models, what I want to compare is super quickly is that how the linear regression, rigid and hover, has improved the root mean square from 0.66 to 0.09, just because what we have done is we have changed the algorithm. And what we have changed in the algorithm, we have only changed the pre-processing, which is basically, if I can scroll up, which are these items. So we're combining real items, removing the correlations, and binning the features and things like that. Okay, perfect. So the compare model is a great function to understand which models are performing the best. So once you know which model is performing the best, you can use create model function and create that particular model from scratch. So what I'm going to do is I'm going to say a create model decision tree, and this is a keyword for decision tree. If you're not sure how to get that, you need to do is you need to say models, and this will give you the ID. So LR for linear regression, LAR for least angle regression, and things like that. So just use that. Create a decision tree model with 4 equals to 5 for cross validation. Okay, so I'm going to run this, and then you will see that we are creating a decision tree with 5 different folds, and then you see the mean here, right? So we have got a decision tree, which is great. We can also do some sort of cleaning in our regression model. So I'm going to say create a random forest model and round everything to 2 decimal points. So when I run this, you should see that the matrix that we're going to print out will have 2 decimal point rounding. But if you look at here in the decision tree, by default it has 4 decimal points. As you can see, now we have 2 decimal points. Okay, let's create one more model, and we're going to create a KNN model. Here we are not defining any fold or any of the round. So you see by default it takes 10 folds for cross validation, and it goes for 4 decimal points. Okay, perfect. So once we have all these models, we would like to tune the hyperparameters of the model. And in the previous tutorial of regression, the beginner level, we learned how to automatically tune the hyperparameters using some predefined grades. Here in the advanced section, I want to talk about the n_iter parameter that we can pass for tune_model. The n_iter is the number of iterations with a random search grid, which basically means that for every iteration, the model randomly selects one value from a predefined grid of hyperparameters. By default, the parameter is set to 10, which means that there will be maximum 10 iterations to find the best hyperparameter. So when we increase the n iterators, it basically means that performance will, or maybe it can increase. However, it could also take more time, right? So here it is, and we're going to tune our KNN model with default parameters, which is 10 iterations to find the best hyperparameters. So when we run tune model on KNN, you should see that the mean value for R square is 0.65. Now let's try and improve this by increasing the number of iterators. So for this example, I'm going to use tune KNN2 for 50 iterations. As you can see that with 50 iterations, it did take a bit of a time to tune the model, but you can see that the R square has been improved from 0.65 to 0.67. Right, with just one line of code, we were able to improve it by 20 base points, which is great, right? Did you know that we all have been using assembling all our lives? Let me prove it to you. Here are 3 products, earphones to be specific, of almost same price range. Which one would you buy? This one, right? But why? Well, the simple answer is that all of these 3 products have 4.5 star ratings, but this one in particular has 222,000 people giving 4.5 star rating. Hence, we are reducing the error by averaging out the number of reviews, right? Well, honestly speaking, that's all assembling is in real life and in machine learning. Wait, that doesn't mean that video is over, because there are many nuances when it comes to applying assembling in machine learning. And that's what we're going to talk about in this video, theory and practical both. So once you have gone through the 6-step framework and developed a model that you think is the best model, it's time to tune the model and make it awesome. So what is model assembly? Well, when we assemble models, we technically train our models in different ways with different parameters such that the final prediction has less error overall. So the first method is called bagging. Here's a simple analogy to understand the bagging methodology. This is our entire data set. So this is the initial data set. When we run bagging methodology, what we do is we pick a random subset of the data from this bigger data set, such that the smaller data set technically, or let's say conceptually, represents the entire population. Okay, so what we do is we pick samples with replacement, something like this. So as you can see that from the bigger sample set, we have picked up a sample of 5, and those sample happens to be 10, 2, 3, 12, and 3. And notice how 3 comes twice, which basically means that once we pick a sample, we do not remove it from the initial data set, and hence, sampling with replacement. And we do this multiple times. And once we do this, we will create multiple subdata sets, and we will train multiple models on these subsets of data. And this subset sample is also called bootstrap samples, if you may. Okay. So let's see this conceptually, and then we're going to jump to Google Colab and do this practically using PyCaret. So assuming we wanted to predict the value of this house, so we're going to take a regression example. We will run machine learning algorithm on each of the data set, and finally, we get 4 different models. I'm calling it M1, M2, M3, and M4, right? Then we make the predictions using those 4 models to get the estimate price of a house. Once we have that, what we're going to do is we're going to take these 4 values, average them out to predict the final value of this house. Beautiful, right? Let's see all of this in action in Google Colab using PyCaret. Perfect. And now is the time to talk about assembling a model. So now is the time where we go into the meat of the examples. So what I'm going to say, create a decision tree. So I'm going to create a decision tree model. So once we have this model, we have R square of 0.95, which is amazing. We've got mean MAE of 592, which is great. What we will do is we will just simply go and say, hey, use this function called assemble model and use the decision tree model that we just created and give me a back decision tree, just like that. So I'm going to press Control Enter. And again, you should be able to appreciate the beauty of PyCaret here, that with just 2 words, not even a line of code, we are able to achieve bagging assembly for decision tree. And you can see that definitely the MAE has improved quite significantly, I would say. From 952, we came down to 846, and R square has gone up to 0.96. Amazing. And you can always check the parameters of what this back decision tree has. So if you want to go through it, if you want to understand what are the details, so here it is. And now before going and talking about how we do boosting assembly, let's quickly see what it means to do boosting assembly conceptually. The second method is called boosting, and it is the most confusing one. And I will put a link in the description where if you want, you can go through the maths and the details. But here in this video, I'll explain how it works intuitively. Because remember, machine learning algorithms are already written for you. You just have to use them. Therefore, although understanding the math is essential, however, understanding the intuition, I think, is more important, right? So let's go and dive into that. So let's take a classification example where machine learning should predict if someone has a COVID-19 virus, yes or no. So the red ones are yes, and the blue ones are no, okay? So we will start with the entire data set and run a desired machine learning model on it. After the machine learning algorithm finishes, assuming our model predicts following results using a vertical decision boundary. In the boosting assembling methods, we now use this model, which technically gave us 2 errors. So it wrongly predicted 2 items. So the red one is in the blue section and blue one is in the red section. So what we will do is we will now use this particular model that we got with 2 errors, and then we're going to run an iterative machine learning model on top of it. And hopefully the resulting decision boundary will result in less error. And we keep doing it as long as we think that we can achieve better results. Let's see this in action in Google Colab, and you're going to love this. I remember when I started learning machine learning, I was very confused trying to understand which algorithm to use and how to code for this algorithm, how to use scikit-learn. But thanks to PyCaret, all of those things have been taken care. And now I can focus on what a machine learning practitioner should do, which basically understanding the data and figuring out how we can best pre-process the data, right? Anyway, let's switch to Colab. And as I said, you're going to love it. It's just 1 line of code, not even a line of code. You use the same method, assemble model, decision tree, and then you just specify the method. So by default, it uses bagging. But if you say, hey, I want to use boosting, sure, just run this code and it will give you a boosting decision tree. The mean has improved for sure, but not as much as it improved in the bagging section. So we're going to try a boosted decision tree. We're going to assemble the model, of course, but with more estimators, and of course method has to be boosted. Seems like we did not achieve better results. So far, the bagging assembling methodology gives us the best result. There's another way of assembling models, which is called blending. So let's understand the intuition behind blending, and then we're going to talk about. I think you already know how we can use it in PyCaret, but for the sake of completeness, let's do this. So blending, as name suggests, is basically blending different models. So the way we do is, you remember our initial data. When in the blending, we do not take a subset of our data. We use all the data to train, let's say, 3 different models. Once we train all the 3 different models, what we can do is, assuming we want to predict the value of this house, as a last step, we use the entire data to train the 3 different models, of course. And at the final step, where we predict the value, we will predict the value of this house using these 3 different models. And then we'll just take an average. And hence, blending is the most intuitive, simple, and practical approach of all, as far as I'm concerned. Let's see how we can do blending in PyCaret. So if I go back to my Google Colab, it's absolutely brilliant how this has been designed in PyCaret. I cannot say this more. So I'm going to just train 3 different models. So light GBM, decision tree, and linear regression. So once we have trained all these 3 models, what we're going to do is simply we're going to say blend models and use these 3 models. With this, you should be able to notice that you can actually provide not just 3, but many more. In the interest of time and keeping the example simple, I'm just using 3 different models. And I think that should be good enough in your practical examples as well. I'm going to run this. And then we will see how the Blender model performs. Blending seems to be working way, way, way better. And this Blender model is not even hyper-tuned yet. So what you can do is, once you have this Blender model, you can go on and you can basically hyper-tune the model, or what you can do is you can use the blend model on the top 3 models that we got from the compare model function that we ran at the very starting of this tutorial. So if I go up, came quite far. There it is. Okay. So when we blend top 3 models from our compare models method, we got even better results of less MAE and even higher R2. Last but not least, when you're working on any of the machine learning project, you have to do a lot of experiments, which basically means you would also like to log different types of whatever you have been working on. So if I go to my file, I have logs.log. And you can see that whatever I have been doing has been logged into this file, which basically means is that you can use any of the visualization tools, for example, MLflow, see how you have been performing, how your experiment has been going. So I've started the MLflow. For some reason with PyCaret, this functionality is not working. So if they fix it in future, that would be amazing. Otherwise, you can use any other visualization tool for that matter. As a wrapper and next step, I would like to ask you a couple of things. And the craziest part will be that I'm going to ask you to like this video if you have learned something. Subscribe to the channel if you haven't done it already. One thing that you can do is that you can share it with one of your friends who you think might benefit from this tutorial. And as you know that I love interacting with you guys, so if you leave a comment, what you like, what you did not like, that would mean a world to me. And always remember that giving a like, sharing, and commenting to the video is zero cost effort that you can show to support this channel, okay? I think that's all for this video. GKB signing off until next week.